Hi, and welcome to Lecture 4. So in this lecture, we're going to extend our discussion of analysis of variance from Lecture 3 and talk about repeated measures designs. Before we do that, we need to remember some of the big ideas that we learned in Lecture 3, namely with single factor analysis of variance. So to do that, I just want to recall the data set that we used last time. And here we had an industrial organizational psychologist who was looking at computer designs and was recording the number of errors that were done by 5 people in each of 3 independent groups who each were assigned a different keyboard. And you can see here that we had keyboard 1 seemed to come out on top, right, because it had the smallest number of errors. And we wanted to come to that conclusion with a nice consistent way of looking at these data. And the way we did that was with the analysis of variance. And that came because what we wanted to do was take a look at this data and make some sense of it. And one of the things that we mentioned last time was that in terms of experimental design, data are nonsense unless you have some sort of underlying model to impose structure. And we called structure a data story. That is, we think about how can we generate each of these data points. Now, you might also remember that what we did was we thought about this data story as being, well, you could start by taking the mean of each group, and then to get each of the data points, you just add some bit of residual error to account for each of the data points. I want to take that idea here, though, and take it just a little bit of a step further to get a slightly more sophisticated data model that's going to be really useful when we jump to repeated measures designs in a few moments. So the underlying linear model is going to look like this, and we'll go back to the picture to explain this in just a second. We're going to write it in this form. We're going to write each data point xij. Remember, the i's and j's are indices to reflect participants and experimental conditions. Well, they're going to be thought of as this. We're going to write it as mu plus alpha j plus epsilon ij, where what are these things? Well, the translation is this. Each score can be attained by starting with the grand mean mu, all right? So the grand overall mean of all the observations. And then adding a relevant treatment effect. What is the effect on the grand mean of being in group 1? And then what is the effect of being in group 2? And then what is the effect of being in group 3? And then finally, once you've done that, adding the remaining what we call residual error. And this is just error that's not accounted for by mu and the treatment effect alpha j. So let's see what that looks like in our data up here. Well, first thing we need to know is what is the grand mean. And we can easily compute this. Since this is a balanced design, we can compute the mean of the 3 means. And that's just going to be 12 as a sum divided by 3, which gives us a grand mean, I'll write it this way, of 4. Okay. And so what I'm going to do first on my plot is I'm going to move this little dashed line up to 4. Okay. So that is going to be the simplest possible model of the data. That is that every keyboard design has a mean of 4. Well, that's not exactly a great model because as we can see, that doesn't seem to capture the overall trend that I'm seeing in the data, which is that the errors sort of increase, if you want to think about it that way, as I go from keyboard 1 to 2 to 3. So the way to account for that increase is, well, let's figure out what the treatment effects are. And what we mean by that is, what do I have to add to this grand mean to get the condition mean, right? So if I start with a grand mean of 4, how do I get to a condition mean of 1 for keyboard 1, right? How do I get to this thing right down here? Well, what I have to do is I have to subtract 3. Right? And so what I would say here is that my treatment effect is minus 3. Okay. Now, let's do the same thing for keyboard 2. Keyboard 2, the mean was 5. So I'm going to draw that here. How do I get from the grand mean at 4 to a treatment effect of 5, or a treatment mean of 5? Well, I add 1, right? And so that treatment effect is a plus 1. And then finally, how do I get to the condition mean of 6 for keyboard 3? Well, similarly, I have to add 2. And so now what you can see is that I have decomposed my data into keyboard 1, I start with a grand mean of 4, and then I subtract 3. And that gives me an estimated error of 1 for people in that group. And then for keyboard 2, I start with a grand mean 4, and then I add 1. That's the treatment effect. And that gives me an estimated errors of 5 for that keyboard. And then finally, for keyboard number 3, I start with a grand mean of 4, and I add 2, right? That's the treatment effect, to get an estimated number of errors of 6 for keyboard 3. Now, of course, not everyone in those groups, or particularly in group 3, has 6 errors, so that's where the residual error then goes from here to here, and here to here, and here to here. We're not going to draw those here, but that's the model is accounting for the rest of that variation as just what we call extra or residual error. So what we've done here is with this grand mean of 4 and these individual differences, that is, we call them treatment effects, is we've got a way to estimate our model, okay? And it looks like this. We would write the full model in this form. We would write it as mu plus the alpha j's plus the epsilon ij's. And we can actually estimate what mu is. It's the grand mean. And then for the alpha j's, well, it's a different treatment effect for each condition. Right? It's a different for each keyboard. For the first keyboard, it was a -3, right? Because 4 minus 3 gets you the mean in that group, 1. For the second keyboard, it was a +1, because 4 plus 1 gives you the mean in that group, which was 5. And then finally, for the last keyboard, it was a +2, giving you 4 plus 2, or 6, for the mean in that group. And so when I say write the full model, this is what I mean. Write it out like this, and then estimate what you can. Now, what's this all good for? Well, it doesn't really give us much on the work that we did last week, which is why I didn't introduce it then. But for what we're going to do this week, it becomes very useful to think about these effects and how to estimate them, because it's going to change how we analyze our data. It's going to change the nature of our analysis of variance. So what is it that we're talking about this week, you might ask? Well, we're going to talk about designs where participants are measured multiple times. In the previous data, everybody was measured once, right? Everybody was put in either keyboard group 1, 2, or 3, and then they did the experiment and we counted the number of errors. But now let's consider what are called repeated measures designs, where you have someone who comes in for a pre-test and a post-test, or maybe they're doing an experiment and they have like 3 or 4 different conditions under which they're performing the trials in that experiment. So repeated measures designs are extremely common, especially in cognitive psychology, but in lots of other fields as well. So how do we handle these repeated measures designs? Well, that's the purpose of the lecture. Let's figure it out. So here I've got some data, and the data are as follows. I've got 12 observations that came from 3 subjects, and I've labeled them as S1, S2, and S3. And these 3 subjects each completed 4 different experiment treatment conditions, which I've labeled as A1, A2, A3, and A4. And so you can see here that subject 1 contributed 4 measurements, 5, 8, 8, and 7. Subject 2 contributed 4 measurements, 3, 7, 5, and 3. And then subject 3 contributed 4 measurements, 1, 3, 2, and 2. Now, of course, our question is, are there differences among the treatment groups? Okay, are there differences among these conditions, A1, A2, A3, and A4? Not, are there differences in the subjects? How do we answer that question? Well, that's what we want to figure out now. Let's look at the data. Okay, we can always do that. And if we plot this, I didn't actually put a legend up here, but the solid dot is going to be subject 1, the triangles are subject 2, and the X's are subject 3. Okay. Now again, remember, all data are nonsense without an underlying model, but by putting these subjects with different markers, you can kind of see that there's a lot of things going on here. Particularly, you can probably see that, there's some vertical separation between the subjects. There's always subject 1 scores higher than subject 2 scores higher than subject 3. It's not always by the same amount, right? They're a little closer here and farther away here, but certainly subject 3 is all on the bottom, subject 2 is all in the middle, and subject 1 is all up here. In fact, if you were watching the trace of my pencil then, you might have seen a pattern similar to this going on. Let's see if I can do this. You might have seen a pattern similar to that going on, not only for subject. Let me do this right here. Hang on 1 second. Sorry about this, guys. I'm clearly not able to do what I'm thinking that I want to do. Here we go. So you might notice a pattern. It kind of goes up and then down, right? So as you go from A1 to A2, you increase, and then going down to A3 and A4, you're decreasing. And it seems to hold for subject 3, seems to be a pretty good fit for subject 2, and it seems to be a pretty good fit for subject 1. So what we're seeing here is not only variability in the conditions, but also variability in the subjects themselves. So how do we handle all of this? Well, as before, we need to think about what is our data story. So I just mentioned not only is there variability between these treatments, but we've also got some variability between the subjects that we might want to account for. We've got some insight onto how to do this. We can just extend our model that we used in the regular old ANOVA, right, the single factor ANOVA, as this. Let's start by, let's start just like we did before with a grand mean mu. Okay, so some overall mean of all the data. And then, of course, just like with the regular ANOVA, we'll add a treatment effect, alpha j. There's going to be 4 treatment conditions here. But then let's also add in a subject effect, and we're going to call those pi's, pi for p or participant in this case. So what's left then, of course, is the residual error. So what's new? What's new is this part right here. We're adding a subject effect. We're accounting for or modeling the variability between subjects as well as the variability between the treatment conditions. This is exciting. How do we do this? Well, let's write out the formula. Okay, the formula will look very similar to the last example that we did, except for one thing, and it'll be that little pi I term. It's still mu plus alpha j plus the epsilon ij's, but this guy right here, this participant or subject effect, is new. So what I want to do first is talk about how to estimate these effects from the data. We did that in the single factor design just a little bit earlier. Let's figure out how to also estimate the subject effects. And we're going to do this by considering the marginal means. So what I have done is just copied that table back over here, and I've made myself a place in the margin to compute the means. Okay? So some of these will be easy to do in the head. If not, we'll pop a calculator up and do them, but let's just work these out together. So first of all, let's do the treatment means. So we'll look at each of these columns and write the means down. Okay, so the first column, we have 5 plus 3 plus 1, that's 9, divided by 3, which gives me a marginal mean of 3. For the second column, we've got 8 plus 7 plus 3, which is 18, divided by 3, which gives me a marginal mean of 6. Okay. For the third condition, we've got 8 plus 5 plus 2, which is 15, divided by 3, which is 5. And then finally, for the fourth column, we've got 7 plus 3 plus 2, which is 12, divided by 3, which is 4. So there's that up and then down pattern that we saw in the graph. Now let's we'll use this to find the marginal means, right? So this is a balanced design, so there's an equal number of observations in each experimental condition. So we can simply take the average of the means themselves. So this is 3 plus 6, which is 9, plus 5, which is 14, plus 4, which is 18. We take 18 divided by 4. We don't get a whole number, but we get something reasonably easy to deal with, which is 4.5. So there's the grand mean. I'm going to highlight that because we're going to need that a bit later. Now from the grand mean, we can compute the treatment effect. How do we do that? Well, let's do this in red. And I'm going to write down here alpha j. Now, what we do is we take the mean, okay? We take this mean and we subtract the grand mean. So if we take 3 minus 4.5, that gives us a treatment effect of negative 1.5. What does that mean? That means to get this condition mean, you have to start with the grand mean and subtract 1.5. So the treatment effect is what do you have to change the grand mean by to get the individual treatment mean. So we can do the same thing for all four of these. We'll take 6 minus 4.5, which is a plus 1.5. Okay. We'll take 5 minus 4.5, which is a plus 0.5. And then we'll take 4 minus 4.5, which is a minus 0.5. So there we have our four treatment effects. Remember, the treatment effect is what you have to change the grand mean by to get the treatment mean. Okay, so this is all just like we did in the first example. What about the participant or subject effects? Well, we do those the same way. We're going to find the marginal means, and then we'll find the subject level effects from those marginal means. So let's do the marginal means first. Marginal mean, remember, we take now the mean of this row, and we'll write it here. So let's do that, and we'll do that in blue. So for subject 1, we've got 5 plus 8 plus 8 plus 7, which is turns out to be 28. Divided by 4 this time, it's going to give us a marginal mean of 7. So subject 1, on average, scored a 7. Subject 2, we'll do the same thing. We'll take 3 plus 7, which is 10, plus 5, which is 15, plus 3, which is 18, divide by 4, and we get 4.5. Okay. And then finally for subject 3, we take 1 plus 3 plus 2 plus 2, which is 8, divide by 4, and we get a marginal mean of 2. Now what do we do with these? Well, we want to estimate the subject effects. So what do we have to change this by to get from the grand mean down to the subject mean? Well, just like before, we'll write pi I here for our estimate of the subject level effects. And just like before, we'll take the subject level mean right here, and then we'll just subtract the grand mean. Okay, so this will be a plus 2.5 when we take 7 minus 4.5. Now what that means is to get subject 1's mean, you have to start with the grand mean and then add 2.5 to get that right there. That same reasoning is going to give us a 0 for this subject effect, because that says that you start with the grand mean, 4.5, and add nothing to get that subject's mean. And then finally, what do we have to add to 4.5 to get 2? Well, we actually have to subtract 2.5. Okay. And so there we go. One of the things you'll notice is if you do this right, then the sum of these effects will be 0, and it certainly is here. Same thing here as well, right? Every one of the effects balances out to give you a sum of 0. So that's what we've done so far. So what we've basically gotten here is that we can write our model just like before. This time we're, of course, adding the subject level effects, and we can estimate them. We have 4 treatment effects, these right here, and we have 3 subject effects. So we would write that in this manner. We would have our grand mean of 4.5. We would have our 4 subject effects written in this vector, which is what that's called. And then we would have our 3, I think I said subject effects. I meant treatment effects here. Our 4 treatment effects and our 3 subject effects, the pi i's. Okay. So there we are. We've estimated the model. Now, why do we do this? Beyond some interesting exercise. Well, we do this because now you'll be able to see here in just a second that we've essentially been able to isolate, of all the variability in these data up here, we are now able to isolate what we really care about, and that is, are there differences in these means? If you look at all these data together, it's actually kind of hard to see that there's differences in those means, and you'll see why at the very end of the lecture. But if we're able to estimate what the contribution of each individual subject is, then we can more easily see what the contribution of each treatment condition is. And particularly, we can test whether these treatment effects are 0 or not. Okay? So when we're thinking about hypothesis testing, that's what we're asking. We're asking, are these guys, these alpha j's, equal to 0? If you've got a null hypothesis, right, you're literally saying there's no effect. And in the language of this modeling, that would mean that this effect vector, these treatment effects, are nothing. They are 0. So when we write a null hypothesis for any ANOVA, it's actually very easy to write it if you use this kind of notation. In this case, we call this a constrained model. That's not too important here, but you'll see that language used quite a bit today and in your homeworks. So hypothesis testing, you know how this works, right? You start with a null and you have an alternative. The null is that the alpha j's are 0. And the alternative is that one of them, some alpha j somewhere, is not equal to 0. And we want to know which of these better predicts the observed data. Our tools for that will be the same. We'll use the p-value and or the Bayes factor, but we need to figure out how to compute those. And we're still going to use ANOVA to do this, but it's got a slight twist on it. So let's recall how ANOVA works. ANOVA, or analysis of variance, works by partitioning the variance. So remember, we take our total variance and we split it up into the variance between the treatments and the variance within the treatments. And if we take the ratio of those two, the variance between the treatments divided by the variance within the treatments, that gives us the F ratio. Remember F for Fisher, who invented this technique. So what do we do when we've got repeated measurements? Well, in repeated measures designs, we start the same place, right? We've got the total variation or the total variance split into this variance between treatments and this variance within treatments. But the variance within treatments has another source. Particularly, we're going to split that into not only, well, we're going to split that variance within treatments into variance between the subjects themselves and then what's left over. So it's kind of a further partitioning. And then what we're going to do is we're essentially going to ignore that variation and then compute our F ratio by taking the variance between treatments and then dividing by what's left over, this residual variance. So the F ratio is written slightly different here. It's still the variance between treatments, but then we're going to divide only by that residual variance that's left over after we account for the variation between subjects. So that's the interesting twist that repeated measures ANOVA does. Essentially, it makes it a more crisp, more reliable way to see the variation between the treatments. You've essentially collapsed or gotten rid of the subject level variation. On the graph, it's going to be a little hard to show you this, but on the graph of these data, what you're essentially doing, I got to go up here to do it. What you're essentially doing is you're taking these patterns here, and let me do it with this. You've got that little pattern there, that pattern there, that pattern there. That's showing you that you can literally just squish those all together, and they're showing basically the same up-down pattern. When you squish them together vertically, what you're doing geometrically is you're removing subject variation. It's a brilliant idea, and that's really what's going on under the hood with repeated measures ANOVA. It's just a brilliant geometric argument. So let's figure out how to do it. Okay, so we've gotten our estimates of the subject level effects, but now let's actually do the hypothesis testing part. So as we just mentioned, the hypothesis testing part means we've got to find one more bit of variance. We've got to split this up into between subjects variance and then what's left over. Well, how does this work? Well, just like before, we're going to calculate the same things. We're going to calculate the total sum of squares, which you'll remember is the sum of the x squareds minus the sum of the x squared over n. We'll also find the sum of squares between treatments. So this time that's going to be 4 different differences between the treatment means and the grand mean. And then also, we're going to do the variance between subjects. So that means that we need to compute the sum of squares between subjects. Now, that's going to be done exactly the same way. It's going to be n times the sum of the subject level mean minus the grand mean. Okay. You'll notice in the notation here, in the last lecture, we would have just said x bar j for the mean of group j, but you'll notice now, to make it really clear what we're talking about, I'll write like treatment j, so that you know these are the treatment means. And then down here I'll write sub I, because I want that to be the subject means. Okay, so let's figure out how to do this. Let's actually work some examples. And of course, once we do that, what the residual variance is just going to be what's left over. We'll take the SS total and then subtract those two things out. Okay. So let's do the example. And we're going to work these together. Okay. So let's start with the sum of squares between treatments. So there's the formula. Now there are 4 observations in each group. And then I want to take the difference between the group mean and the grand mean. So just remember, let's put these in our memory. These data, sorry, I got a long way to scroll up here. These data, the group means were 3, 6, 5, and 4. All right, there were these guys right here, 3, 6, 5, and 4. So let's go back and write those in, 3, 6, 5, and 4. So this is going to be 3 minus the grand mean squared, plus 6 minus the grand mean squared, plus 5 minus the grand mean squared, plus 4 minus the grand mean squared. Okay, we need to figure out what all those are. So that's going to be 4 times. So this is going to be minus 1.5 squared, which is 2.25. And then this one's going to be the same, 2.25. This one will be a half squared, which is 0.25. And same thing here. And if we add those up and multiply by 4, it turns out that we get a total of 15. So the SS between treatments is 15. Now that's, you know how to do that. That's from last week. We also need to do the same thing with the subjects. So we need to go back to our data table and remember what the subject means were. Okay, so here they are. The subject means were 7, 4.5, and 2, respectively. So let's hold those in our memory and go back and work out the subject's level sum of squares. Here we go. So this is going to be, now in this case, each of these subject means had, hang on guys, I totally need to go back and fix something. This was a fundamental error on my part, and it's the role of this n here. I am so sorry. So the n is going to be the size of whatever the group that gives you that treatment mean is. Okay, so these treatment means each came from 3 observations. All right, if you look at the data table, the treatment mean of 3 and the treatment mean of 6, etc., they came from 3 observations in each column. So what that means is I'm going to multiply by 3. I need to scale up to reflect 3 observations. So that means I need to fix these things up. I was looking on my notes and just totally messed up that. That's 3 and that's 3. This product, if you were working along, you're probably trying to figure out where did I get 15. That's because it's actually 3 times that sum. So this sum right here turned out to be exactly 5. 3 times 5 is 15. Sorry for that lack of clarity there, but that's exactly what happened. We did get the same answer in the end. Now, the reason that popped up is because I'm thinking, okay, what's in here? It's going to be slightly different. The subjects, remember, there were 4 observations for each subject. So that means that I need to multiply by 4. And now I'm going to take my subject means, which were 7, 4.5, and 2, and I'm going to subtract those from the grand mean. So this is going to be 7 minus 4.5 squared plus 4.5 minus 4.5 squared plus 2 minus 4.5 squared. Okay, so it's done just like the sum of squares between treatments, but this time it's the subject means. And now if we figure those out, this gives me 4 times. Okay, so this difference here is, the first one is 2.5 squared, which is 6.25. The second one is just 0 squared. And then the third one is the same, 2.5 squared. So that's 6.25. And if I multiply those together, this will be 4 times 6.25 plus 6.25 is what? Well, let's do it on the calculator real quick. 6.25 plus 6.25 is 12.5. And so 12.5 times 4 is 50. Okay. Oops. Here we go. All right. So our sum of squares between treatments, our sum of squares between subjects. Again, note that the n's are different in these. So you have to think about, for these groups, for these things you're taking the means of, how many observations gave you those means. And then finally, we find the sum of squares total, just like we would have done last time. I've already gone ahead and done that for us, just to not have any errors on the video. that I already made an error just a second ago, but that turns out to be a total of 69 for the sum of squares total. So we work out the ANOVA table. I've gone ahead and translated these things into the ANOVA table. Okay. So the sum of squares between treatments is, hang on one second, there we go, is 15. The sum of squares between subjects is huge, right? It's 50, and then the total was 69. So what is the residual? Well, the residual is everything that's left over. So the total sum of squares is 69, and 50 plus 15 is 65, so that means that the residual sum of squares is just the remaining 4. So that's not much. Now let's do the degrees of freedom. Degrees of freedom is pretty easy to think about. I like to do it this way. Between treatments, well, I've got 4 treatment groups, so that's 3 degrees of freedom between the treatments. Let's skip residual for just a moment. Let's go to between subjects. There were 3 subjects, so that's 2 degrees of freedom there. And then total, well, I take the total number of observations, which was 12, and I subtract 1, and I get 11. What's left over? Well, what's left over then has to be 6, because those 3 need to add up to 11. Where does 6 come from? Well, basically, it's the number of conditions minus 1 times the number of subjects minus 1. So that gives you 3 times 2 in this case. But if you do it kind of working backwards, you'll always get it right. Now, once we've got the mean squares, once we've got the sums of squares and the DFs, we can find the mean squares by dividing. So 15 divided by 3 is going to give me a mean square of 5. So that's the variance between treatments. The residual, well, that's going to be 4 divided by 6, which is about 2/3 or 0.67. And then the variance between subjects, that's going to be 50 divided by 2, which is 25. So basically what this is saying is a lot of the variation that we were seeing in that data is due to the subjects, not the treatments themselves. But once we factor out all of that between subjects variation, finding the F ratio, remember the F ratio is just these 2 divided by each other, I take 5 divided by 2/3 and I get 7.5. Okay. And that's a fairly reasonable F ratio. If I plug that into my calculators, it turns out I get a p-value close to 2%. I get a pretty big Bayes factor of 41 or so for the alternative. So it looks like there is a difference, and there it is. You'll notice that once I get to this stage right here, I completely ignore the between subjects variance. That's because it doesn't factor into the F ratio. It is simply there to get a more crisp estimate of the between treatments variance and what's left over. So the role of estimating those subject effects is just to get a handle on the subject variance. Okay, and then you throw it out. So we could end here, but I want to show you why you would even care. Why you would even care about doing a repeated measures ANOVA. So the question then is, what if we didn't account for that subject variability? Okay. Well, I've taken the liberty of redoing the ANOVA for us. Now remember, Remember the total sum of squares was 69, and remember the between treatments SS was 15. So that means that everything left over, if we ignore subject variability, is this 54 here. And then if we work through and compute our ANOVA, we get a mean square of 5 again. But this time the residual variance is 6.75 because we haven't accounted for the subject variance. It's just everything else within the groups. And if we do this F ratio, that gives us something less than 1. It gives us 0.74, which, as you can see, is quite evidential for the null hypothesis. Same data, but I don't get the treatment effect here like I do when I account for the subject variability. So the moral of all of this is that by accounting for the subject variability, repeated measures ANOVA is better at uncovering, I don't know why I don't have the word uncover there, but that ANOVA can better uncover these latent treatment effects that we might not be able to see if we didn't do this. So when possible, do repeated measures designs, and then being able to account for that subject variability can be a very powerful technique. We'll see something similar in a couple of lectures when we do analysis of covariance, but it's a slightly different way of accounting for extra variation that might be due to something else. But in a way, this is like the simplest example of analysis of covariance that you could do. So that's all for now. Mostly a technical lecture, but the big ideas here are what is the difference between repeated measures ANOVA and traditional ANOVA. In repeated measures ANOVA, I account for subject variability. That gives me a little bit of extra stuff in the ANOVA table, namely this part, but I essentially ignore it. I just compute the ANOVA based on this. And I get this by literally ignoring this, throwing it out. So that's it for today. If you have questions, of course, let me know, but I will look forward to seeing you at the next lecture.